Thank you, Gunnar.
Okay, well, thank you very much for the invitation to speak. It's really, I'll say it, it's really nice to be back in San Diego again, even if only virtually. So, what I want to talk about today is the way that I view topological data analysis is as a new way to be used with others for mathematical modeling. So let me talk about, now when I think of mathematical modeling, when I hear those words, I typically think of algebra. I think of equations of one kind or another, maybe differential equations, maybe algebraic equations that one uses when one is trying to study. Typically, what I would say is kind of simple, or at least smallish data, and so forth. But I would argue, though, that also clustering can be viewed as a kind of modeling. It's different kind of modeling. In the case of the algebraic stuff, it is that you're modeling things by the set of solutions to equations. And instead, clustering takes the point of view that, well, a partition of the data into groups, into taxonomic entities, is instead also a model. So the question is, what do the models buy you? The models buy you both understanding and actually a certain kind of compression as well. Compression of the data in a way that hopefully preserves some features and is kind of allows for better understanding of it, because we as humans are not able to process maybe tens of thousands of features or as well as we would like. Okay, so now when we think about algebraic modeling, the number of features is typically smallish. I won't say that that's always true, but typically when it works best, they're smallish. And typically also when it's at its best, there should be a theory behind it. There's a theory that says how some of the features relate to the other features. It's not often very expressive for very complex data sets. So if you're someone who's trying to solve questions about fraud or malware and so on, then algebraic ways are typically not ways that you want to try to solve them. They sometimes can do approximate things very well with high degrees, but those high degrees are difficult to interpret. And again, difficulty with kind of discrete kinds of data. There's data whose format is somehow Boolean variables and so on. On the other hand, cluster analysis, is a great thing. It works in many situations. There are some issues with it, though. There are many different methods. Obviously a ton of different methods that have been invented, and typically they're not backed up by a substantial theory. Often requires the choice of a threshold of some type. It does not model continuous phenomena. It explicitly says that you want to divide things into discrete groups. And what I would say is that another problem is that oftentimes one finds that, the outputs of the algorithms turn out to look like they should be soft clusterings instead of hard clusterings. And soft clusterings here means that, well, you divide it up into groups, but you permit overlaps in the groups. So what I want to talk about then is a method of modeling that sort of takes the best of both worlds here. It says, on the one hand, with the mathematical modeling, the algebraic modeling, the data has some kind of shape, and not so much in the cluster analysis. I want to argue that the shape is actually fundamental, but that algebraic methods capture shapes in too rigid a way. So let me talk now about the shape of data. I want to argue that the shape of the data is the first thing that you want to know about the data. It's also sometimes the only thing, but oftentimes you will also need additional bits of information beyond the shape. And so here, if we look at this kind of data that's right here, this looks like it's ready-made for linear regression. And as you can see here, we have a straight line. We're approximating the data by a straight line. When the data actually is well approximated by a straight line like this, that's a fantastic place to be. And so that's what you want to do. You want to apply the linear regression, and you want to perform predictions and obtain the understanding that one often gets with such models. Unfortunately, of course, all data doesn't fit along these lines. So when I have data that looks like this instead, where I've got something where it looks like it's 3 pieces. There's no line that approximates that or is very informative about that, but I can interpret clustering as approximating it by a shape. It's just that the shape is a little different. The shape is not a straight line. It's instead 3 discrete points. You might not think of that as a shape, but it certainly is. And so clustering we can think of in a meta sense as approximating a data set by a discrete set of points, just like before we approximated the data by a line. Okay, but unfortunately, it doesn't end there either. We might hope that we're done, but we're not, because we might have data like this. This might occur when you're dealing with time series and you've got some variables that are undergoing periodic or recurrent behavior. And so in this case, there's this loopy behavior instead, which we can approximate it by a circle or even somewhere irregular loop here. So now, as mathematicians or as quantitative scientists, we might say, okay, I developed linear regression to work on some kinds of data. I developed cluster analysis for other kinds of data. Maybe I should develop a loop detector for this kind of data. On the other hand, I might be getting a little queasy because I'm feeling I'm doing a lot of cases here. And is there any reason to believe that I will be done when I build the loop detector? And the answer is no, because I might have data that looks like this. So it's kind of a Y shape. This might occur, for example, if I'm taking sensors from an airliner, that central part might be, flying at altitude in non-turbulent conditions. And then the endpoints of those various intervals there might be, takeoff, landing, and flying in turbulent conditions. Now again, I might say to myself, maybe I built the loop detector. Maybe I went ahead and did all that work, but now I say, oh, now I've got to do a Y detector. Well, at this point, maybe I realize I can't do that. I need to have some mechanism that covers all shapes, some mechanism for modeling the data that includes all the shapes. And then if I do that, of course, as a byproduct, I get that I have some version of regression, I have some version of clustering, but I have all these other capabilities as well. Okay, and so how am I going to approximate the shape of data? Well, Leonhard Euler foresaw this issue. He was looking at a different context where he was trying to ask, can I cross all the 7 bridges across the river Pregel in Königsberg, crossing each bridge exactly once? And what he found was that there's a lot of unnecessary data in the situation here. So it's the length of the bridges, the size of the islands, the depths of the river. All those things are not relevant. All that's relevant is that network model on the left there. And so the idea is that one can use that network, that simplified network model, to resolve the problem pretty quickly. So the question becomes then, we know that it's true that networks, graphs, oftentimes encode shapes. So, computational geometers, for example, build meshes, which are graphs for surfaces, and so they can encode shape. And it turns out that there's a very systematic way, actually, of taking data and producing shapes, and it's when you have a covering of your data set. So when you've got a bunch of sets whose union is the full data set, but they might not be a partition. In other words, they might not have the property that they're all disjoint sets. So, and here's what you do. So if you look here, we have a set on the left, which is the kind of the frame of a painting or something here. It's covered by 4 sets, 2 of which are red and 2 of which are blue. And so the way that I build a graph out of this is I say, well, I'm going to build a node for every set that's in the covering. So there are 4 sets there, the 2 reds and the 2 blues, and I create those nodes, and then I fill in an edge between any 2 of them that overlap. So notice that the 2 that are antipodal from each other, if I have a point that's antipodal from the other one, in this case, if I have 2 sets that are disjoint, I don't connect them. So in this case, the 2 red ones are not connected, and the 2 blue ones are not connected. And so what I've done here is I had the frame of the painting, but now I've kind of actually got a model for it that is also circle, so to speak. I mean, it's a square, but so we've lost information about the curvature, but maybe we're interested only in qualitative information, as we were in the case of Euler's situation. So this construction, this nerve construction, is quite generic, you know, and one can produce coverings often of sets in many different ways. And every time you do that, you can build a sort of a shape model, which is the graph that you have there on the right, if you like. And actually, we like to dress it up with even further. We build it into a simplicial complex where I can include triangles and tetrahedra and so on as well. So if I have triple intersections, for example, I include triangles. And if I have quadruple intersections, I would include tetrahedra. And now it's getting even closer to, you know, a real honest to God shape. Okay. So what does the nerve construction do? It takes a set with covering as its input. It constructs a geometric object. Actual honest cluster decompositions where the sets are disjoint gives a zero-dimensional complex. So it's a discrete set of points. But you know, now we can actually see that this is actually the right kind of output for soft clustering. You know, soft clustering shouldn't just be a list of soft clusters that we're covering. It should be, we should have some indication of what the overlaps and correlations are. So, and it's a little bit like a Venn diagram. So now I'll show you a particular way of doing this that we came up with and we've used quite a bit, which is called mappers. So this is a way of creating a covering on a data set. So we start out here with our data set, and we suppose that it's equipped with one or more projections to the real line. Now here I've said it's the y coordinate. Typically it's not a coordinate. It's something that's more mathematically, or I should say statistically meaningful, like you know, the density measures or centrality measures. Okay. But in any event, let's suppose here, let's just take this very simple-minded situation. So what I do now is I take the real line and I cover it, the real line, by intervals, overlapping intervals. And they're coded by different colors here. And then what I do is I'll take the pre-image of those intervals. So you'll see here that now I've covered this set. First of all, I have 4 bins, you know, the top, the middle, 2 middle ones, and then the bottom. But now what I do is I perform a clustering step in every bin. I don't cluster the entire thing, but now, and what I cover it by, what I cover the space by, is exactly the various clusters. So I'll call those partial clusters because they're clusters within these bins. And so what I get then is, now as I start to build my nerve complex, I get the 6 points here, the 6 nodes, because I have 2 clusters in each of those middle bins. And so now the overlaps, and you can see those overlaps are nicely encoded there with orange sitting in the top and also orange in the middle. So now I can fill in the edges here. And so that's what we do. This is something systematic that I can do. Just, you know, it only depends on choice of a map or maybe 2 or 3 going out, and it will produce models for me in that way. Okay. So I'm going to give you some examples of this construction at this point. So this is unsupervised analysis of diabetes data set. This is a group at the Mount Sinai in New York studying people diagnosed as type 2 diabetics. And what you can see here is that you find that in fact, you've got 3 distinct groups. And I should say this was about 10 or 11,000 patients, somewhere between there. It turns out that the finding from this paper was that type 2 diabetes is in fact 3 separate diseases. One of them is heavily correlated with cancer, the other 2 are not. And one of them is very much correlated with neuropathy, and the other 2 are not. And so that's an important finding here about the data, because if you are familiar with the notion of precision medicine, one wants to be able to treat a specific disease. And if type 2 diabetes is actually many different diseases, it may be that I can, for some of these, I can only develop drugs that work on one or the other of them. And that's a better, simpler task than to try to build a drug that works for all of these 3 at once. If I have the one that's correlated with cancer and I can treat that one more effectively with something which doesn't work on the other 2, I'm still happy. So anyway, it's an important thing to stratify disease in that way. Another example here is sort of a study of progression of infectious disease. This is from the David Schneider group at Stanford. Here, if you think about a situation where you're taking measurements concerning the immune system and so on, both genomic and physiological measurements, What should the model look like? Well, the model should look like you start out at a healthy state and you move through a trajectory as you're getting sicker and sicker until your immune system kicks in, and then you could return by a different trajectory going back. And so what that means is that you actually get a loopy model like this. The nice thing about it is that the model does not explicitly depend on time. And that's good because oftentimes you won't know when someone was infected. And also people traverse the disease trajectory at different rates. So time is, while correlated, is not tightly correlated with your state. So this is a time invariant way of encoding the state in the disease. And they were able to do some very nice things with this, including predicting who was actually going to make it all the way around and who was not going to survive. Microarray analysis of breast cancer. This was one of the early things that we did. This is a small data set, 272 microarray samples and 1,500 features. The finding here is that you can see the model that the part in the lower right there is a very high survival group. In fact, it's perfect survival in a group where you go, if you look at the group that goes beyond the sparse data there, and it's labeled CMIB. That's about 8% of the patients. It's sort of a new group of breast cancers that was quite interesting to find. Now, but one could ask, so what actually characterizes these groups? So here's an interesting point now. So what I've talked about, the modeling that I talked about here is typically taking the data set and I take the data points, that is to say the rows for the data matrix, and build this model, clustering that or, building this topological model of it. But one could also consider the transpose matrix. So the rows of the transpose are the features. And so I can build a topological map of the feature space instead. And what's interesting is that each row of the original matrix gives a function on the feature set and therefore on the topological model by averaging, it turns out. And in fact, if I have cohorts here rather than individual data points, I can also color by them by the average. And so now what you can see happens here is cohort A, which was the perfect survival group. So what I'm seeing here is the same graph in all three places, but the functions that the data points are are shown here. So this is cohort A, which was the perfect survival group, and you can see that it's very blue in the lower part and very red in the upper part. Now the second one, cohort B, that's the upper right in the previous picture, which actually is a very it's a bad prognosis situation. And you can see that it's dramatically different. The coloring here is dramatically different. Where it was blue before, it's red now, and then where it's red before, it's now blue. Except there's a collection of bright red genes even up there at within that region that don't seem to change no matter which cohort you use. And then cohort C is the one that's on the was on the far left there, and it looks kind of like a weaker version of cohort B. My point about this is that this is a very useful and interesting way to get your hands on data that's very high dimensional. Because you see here, in this case, it's 1,500 features. We can do sort of, two-dimensional scatter plots to try to understand, pairs of variables. But in fact, that's not what that's a difficult road to hoe. And so sometimes what you do is you will list all the variables by their p-value as far as, say, survival goes. And so one could do that as well. But that's just a very long list of genes, 1,500 genes here, very difficult to interpret. Whereas here, it's pretty clear that what's going on is two things. There's two groups. There's that blue switching to red and the red switching to blue. And so they can look at all those genes. And this is a common feature in a lot of data where there's many, it's not a single cause for anything. It's a lot of things acting in conjunction with each other. And now just one of your colleagues down at UCSD is a fellow named Larry Smarr, who studies the gut microbiome in humans. So in this case, this is the gut microbiome. This is the feature space here for that, a topological model. And on the lower right, we colored by ulcerative colitis. On the lower left is healthy. And you can see that the ulcerative colitis is really characterized by that one group that's circled with on the lower right with a black loop. On the other hand, in the upper right is Crohn's disease. And what you can see is that Crohn's looks pretty much like the healthy one, except it's missing a bright red part that is in the the top of that healthy one. So anyway, useful way to look at things. I'm running a little slow here, so I better move along. Let me give you one important fact about this methodology. So here's a graph. This is sequence data from 3 populations, gene sequence data. Copy number variation is the variables here. So there are 3 populations, Han Chinese, Caucasians from Utah, and Igbo population from Nigeria. So the Chinese one is the red one on the left, and the other 2, I forget, I think the yellow is the Nigerian and the blue is the Utah, the Caucasian. Now, any method that calls itself a method for data analysis can recover these clusters. It can find the groups. No problem about that. But what you'll notice is that the model also sees that there appears to be something slightly different about the Chinese sample. It looks more carpet-like. It's not as high degree, whereas the other 2 are very stellated. And the reason for this turns out to be, it's no biological reason. It's the way the data was handled. So in this case, the data, in the Chinese case, there was a pre-processing step which removed all parent-child pairs. So if you had a parent-child pair, you would remove one of them. So you only had one from each family. And that turns out to make this difference because that pre-processing step was not done in the other situation. Now, we like to think we're always doing science, but in fact, as you know, when you deal with data, the issues about handling the data are fundamental also. Okay, and so topological modeling here, I'm just talking about its features, so the aspects of it that are important. I'm going to move past that now. Let me see. So now we were looking and we were talking about the shape of data. Now I have so many different shapes. I mean, I can look at them, of course, as we did before, but I need to also be able to measure the shape because maybe I need to be having some steps to determine what shape I should have. And so then it's a good idea to introduce a notion of shape of the data. Now within algebraic topology, there's a method called homology, which is a method developed over the last century for understanding the qualitative structure of spaces. When I say the last century, I mean the 20th century, not the most recent one. For understanding the qualitative structure of spaces. And it produces some signatures in ways that I'll try to give an indication of here. What's happened in the last 20 years, started by Vanessa Robbins in Australia, is that persistent homology has been developed since about 2000 to study sampled situations. In other words, in the ordinary homology, we've got all the points. And here we really, we're going to assume that we deal with a sampled situation. So the way that we measure shape is one does experiments. One tries to toss out a loop like a lasso and then tries to pull it tight. And if you pull it tight, you find that there's an obstacle in there and you're unable to do so. But you're actually, if I have 2 holes like this, I might perform the same experiment and get the same answer if I go do this, or even if I do this. Okay. It turns out that that I could also do this. I could throw this loop where it might go around it twice. So in this case, it's hard to make a count out of this initially. Let me say, so how would I try to count the holes? Well, the first thing is I might say that all this loops, that's infinite stuff. I can't count that at all. But what I can do is I can form an equivalence relation on the loops and say, look, any 2 loops that are homotopic, as it's called, if one can be deformed into the other. If I take those equivalence classes, I get down to something which is discrete, but it's actually still not perfect because they're countable typically, but infinite sets. And so I'm still not getting anything useful unless I recognize that there's an algebraic structure on the set. So there's an algebraic structure because here, this one, let's see, this one right here is the sum of those 2 in this algebraic structure. And then this one right here is twice, the loop that goes around once. So there's actually an algebra in here. And typically the way we'll think about this is that the homology is actually a vector space the number of holes is its dimension. And that turns out to work. These numbers are called Betty numbers. Betty naught is the number of connected components. Betty 1 counts the number of one-dimensional cycles and so forth. So figure 8 here, first Betty number is 1 because it's connected. Second one is 2 because there are 2 loops and a Betty 2 equals 0. And here's the sphere, Betty naught equals 1, Betty 1 equals 0, because there's a loop in there, but I can fill it in. So I'm only counting equivalence classes of loops. But Betty 2 equals 1 because it's a two-dimensional object in itself. Torus, similar to that, and then a two-hole torus here as well. Okay, even a Klein bottle. So how do you define and compute Betty numbers? It turns out the descriptions so far are pretty fuzzy and soft, what I've given you, but they're defined in a very precise way, and it involves linear algebra. Let me tell you about simplicial complexes here. So this is a situation where I've got well, graphs in this case. I've got a triangle which has a loop in it, and I've got a D to E which is not a loop. So if I have this situation here, let me just look at the triangle. Here's the bit of algebra that becomes relevant. So I have 3 vertices and 3 edges. And what I'm going to do is I'm going to build a boundary matrix like this. So the columns are labeled by the edges, and the rows are labeled by the vertices. And I put a 1 in wherever the vertex is contained in the edge. And now it turns out that these are Boolean entries. I'll do math mod 2 if you like. And so it turns out now that the rank of this matrix is 1, which means that its null space has dimension 1. And that means that, and furthermore, it's spanned by the vector AB plus AC plus BC. And if I allow myself to think about addition as union, which is kind of legitimate here, because this is kind of Boolean arithmetic and this is exclusive OR, then you'll see that what I'm looking at is a cycle here. That sum is really a union of AB and BC and AC. So in fact, the null space in this case always gives a count of the number of loops. And similarly, the dimension of there's a quotient space. It's a construction that people are less familiar with, but the quotient space of the row of the column space, in this case, the vector space of dimension 3 by the column space, which has dimension 2. Dimension of that quotient space is 1, and that's equal to the number of components. Okay, so in other words, in this simple situation, we can see that the algebra of these matrices really encodes this geometric information. So now, of course, so what mathematicians did is they souped this up tremendously. They souped it up to where you can count spheres and higher dimensional objects. I won't go into all the algebra on that, but suffice it to say that what you get is you get a vector space for every dimension k. There's a key observation here, which was made by Emmy Noether, which says that when there's a map from x to y, there's a linear transformation from hk of x to hk of y. This idea is called functoriality. It's critical to all computations and applications of the subject, and was discovered by Emmy Noether. So now persistent homology says, well, homology works only when we have complete information. What about when we only have a sample? So is there a way to get this shape information? And the answer is yes. And how do we detect the fact that the data is loopy? This data is loopy. This is what I call a statistical circle. This is important for time series and other situations. Well, what we do is we build a nerve for the check construction, which is the nerve of the covering of the data set by the balls. So it produces this kind of nerve of the covering like this. And what you can see here now is this. When I try to do this, if I take this check construction, suppose that I have this kind of data like this now, and now I find that, yeah, the data looks, the large is like a circle, but there are some small things as well. You can see some small holes here. And what happens is that if I compute the homology of this, I'll get Betty 1 equals 3. It's not what I want. I want Betty 1 equals 1 because that's the large loop. And you might say, well, change the threshold, make the balls a little bigger. If I do that, I can fill them in, but now I get something at the bottom here. And so I now have Betty 1 equals 2. So neither answer is correct, but the one that I want is the ones that persist across the change of scale. So that's called persistent homology. And it turns out that can be made into precise algebra where you can extend homology in this way by studying the persistent features. So output is no longer numbers, that's a price you pay, but they are rather barcodes or persistence diagrams. So the barcodes are unordered collections of intervals. Long bars are to be thought of as geometric features and short ones are noise. So in this case of the statistical circle here, if I take what I would call a Betty 1 barcode, it might look like this, where you see the long feature, the long line, which is the signal for the presence of a loop. And then the short ones are coming from the kind of more noisy stuff that I get as I start connecting points. And just to give you a sense of it, there's another description of the barcode in terms of a persistence diagram, which is often quite useful. So after all, each interval can be thought of as a collection of, as a pair, namely its left-hand endpoint and its right-hand endpoint. And so I can actually plot it in the plane. Now, because the left-hand endpoint is always smaller than the right-hand endpoint, these points will lie above the line y equals x. And so here I've got some pictures of some spaces on the left. The A1 is a statistical circle. I have the barcode, and you also see how you've got that single dot in the A3 diagram there. Same way, if I have got two of these loops, I've got a Betty1 barcode again, and now I'll have two dots at the top there, and then a few things at the lower bottom. In C3 is a cluster decomposition. This is a Betty0 barcode, where all the bars start at 0, and they go and they become longer and longer. So anyway, that's a translation between the various ways of looking at things. And the example I'm going to describe for you will use the persistence diagram view. Now, let me just say here, so what the way that topologists think about homology is that it's a way to detect kind of gross features in data, some gross large-scale structure, small number of large-scale structures. So for example, I can detect a circle or at different scales and so on, a Klein bottle in a space of high-density image patches. So this was one of the first things that we did in this project. We found a nice parameterization of a collection of high-density, high variance patches in natural images. And that's been very useful for many situations. In fact, we're using it now to build deep learning models to compute with images with very good success. So, but all this fits into what I would call a traditional topological view of what homology is all about. Namely, it's about big features. It's about, is there a loop? Is there a sphere, a single sphere that describes it? Can we build a cell structure that decides how the space is built up? But now, so there's actually new uses of persistent homology, which is more along the lines of measuring texture. Texture-like features. So think about, for example, distribution of matter in space or complex materials. So let me give you an example here. So if I have crystals, crystalline structures, what I have then is I've got a bunch of atoms, and maybe they're arranged in a rectangular square grid, or maybe they're arranged in a hexagonal grid, or maybe a triangular mesh, or however one wants to refer to that. So that's in a crystal situation where everything is perfectly regular. And here I should say, I have modified this a little bit by noise, which is why I'm not getting things looking absolutely perfect there on the left. Wanted to demonstrate that there's features that are, kind of stable to small perturbations. But what you'll notice is that for that rectangular grid up there, what you see is that the Betty1, I've got a bunch of fairly long, like, 0.3 length intervals there in the Betty1 barcode. On the other hand, in dimension, for the hexagonal grid, you'll notice that those edges are very much smaller. They're tiny, and that's a real distinction. In fact, what you can think about here is this: that if in the idealized situation, the rectangular grid might be that red dot up there. That's a longer interval, and then the yellow dot is a shorter interval. Okay, so in the case where we're dealing with something that's perfectly regular, what each of those dots corresponds to is actually a bunch of dots that are laid up one on top of each other. So if I actually had the infinite grid, I would have to have more or less a delta function there that captures it. In reality, probably the best way to think of the barcodes is as a distribution on the space. Of points in the first quadrant above the line y equals x. Okay, so now this is an invariant of these kind of more texture-like situations. So what I want to describe for you now is some beautiful work, what I believe is some beautiful work by a fellow named Yasu Hiraoka in Japan with collaborators. So, and he's worked on amorphous materials. So this is situations where there's not a completely regular structure, but nevertheless, people sense that there is some observable pattern to it. And so they have been studied by sort of various ad hoc methods, kind of local statistics, counting bonds and counting atoms and so forth. Also ring counts, which are sort of done, ad hoc here, where you impose a graph structure and you perform a count of the number of rings. It's not satisfactory because it's ad hoc and it doesn't capture hierarchical structure either. So it turns out that the structures of these materials often has a somewhat hierarchical nature to it. So persistent homology gives a systematic way of obtaining invariance. So, and what they did, so in this paper, they applied this to silica glass. So silicon dioxide is a fundamental constituent. It turns out the material has three states. It's crystalline, it's got an amorphous state, and then liquid. And what they do is they analyze the silica glass with persistence diagrams, working on molecular dynamics simulations at various temperatures and so on. So also, and they also did work on other materials such as Leonard-Jones systems and Cu, I think copper zirconium glass. Again, I should say, caveat here, I'm not an expert on any of this solid state physics and so forth, but what I will show you is these pretty pictures, which I think are kind of indicative of how the work will go. So what you can see here is they've studied the three separate states. They've studied the crystalline state, the amorphous state, and the liquid state. So let me call your attention first on the right there. What you can see is that in the crystalline state, it looks like there's just a few bumps, like it looks close to a delta function or close to a point mass, or a couple of point masses actually. So, and that's that's consistent with what we saw a couple of slides ago when we looked at the two different crystals there, and we saw that there were sort of point masses at two different points. On the other hand, the liquid state at the far left, it just looks like it's just concentrated around the two, around the y-axis and around the line y equals x. So there's not that much interesting there. There doesn't appear to be much structure. But what they observed is that when I go to the amorphous state, though, what happens is that these point masses actually turn into curves. So they actually identify three curves and then one point mass in this amorphous state, and also they're able to interpret them. So they're able to see what phenomena is it that's happening locally that create those curves, and so that. And they did the same thing, as I said, in these other situations. So it suggests that persistent homology is a very good tool for trying to look at sort of the texture and the situation where I've got massive numbers of points. So the Betti numbers here, this is not like Betti number equals 1 or 2 or even 5. This is like the Betti number is hundreds or thousands even in these complicated situations. But that nevertheless, by viewing it, taking this kind of distributional point of view on here, one is able to glean information about them. And now they went further on this. They took the barcodes and they observed that from these curves, they could actually determine some hierarchical structure within this data set. They were able to recover something which maybe you all know about, but it's called the first sharp diffraction peak. So when you send some light or some wave through, you get a diffraction, and there's a first peak with it that they were able to recover from the barcode. They also observed that the diagrams were suitably preserved under strain, indicating that they contain information about elastic response. So I found this fantastically interesting, actually, because what it points to is the following. See, there's been, within topology, there's been something that a bit of a backwater that's called shape theory. And shape theory tries to study spaces that are not just finite complexes, but they might be something more like a Cantor set or a Sierpinski gasket, if you've ever seen that. In other words, there are these spaces that have very complex local structure, and the shape theorists have been studying those theoretically, but I think they haven't gotten their due credit from the rest of the topology community. As I say, it's kind of they're kind of outliers. But what this kind of suggests is that actually, maybe that's a whole area of application here. In other words, one should develop, further methods for capturing things that are more like texture and local structure using these topological methods. Okay, that's what I had today. So I will thank you very much for your attention.
Thank you. Thank you for the great talk. So as we said, so we want to make this a lot of discussions. So feel free now to chip in to ask questions, and especially if you are a domain scientist from, say, material science, and if you have specific data, you want to follow up on some of the threads that Gunnar just talked about, it would be great to have some conversations. And I should also say that there are already some questions in the chat window, and thanks, Mikhail, for answering those. Yeah. Okay, so let me see whether you can type in your questions to the chat window, or you can just directly unmute yourself and ask. Okay, so let me start with one while others. So Gunnar, I'm wondering, because I mean, especially in the last piece of work you mentioned, the Yasu's work, where now we're looking at it in some sense the persistent diagram profile because of the data, right? So I want to see whether you have some comments on the statistical treatment of persistent homology, which seems to be utterly important, especially for material data.
It is very important. I will say I myself have not been involved in that so much, but there are a number of people who are working on that and trying to study, for purposes of inference, distributions on spaces of barcodes. So the thing is that there are lots of ways of featurizing barcodes or vectorizing them. So there's something called persistence landscapes, also persistence images, which Henry has been involved with, and also symmetric polynomial point of view on them. So lots of ways of coordinatizing them, and that may be, give some ways of attacking these distributional problems as well. I think the answer is that it's something which is being developed. I don't think it's yet been taken the step to be used in a serious way in actual applications, which I think it should be. And so I think that would be a great step to take that theory that's being built, hopefully find that it's applicable and use it. Yeah.
Yeah. So recently, actually, I saw a paper actually from the material science aspect where they're with the material motivation, they actually develop a Bayesian framework for statistical. For persistent diagrams, and so they can do hypothesis testing. So, so let's see whether any questions from the audience. Right. Another thing that I feel that really related to the material world is that. As you mentioned, the data that we have and where the low dimension, high dimension has shape behind them. And topology kind of give us a way to sometimes make sense of this or model this structure behind them, especially when data lies in the high dimensional space. Okay, right. So for example, I could envision that one look at the space behind, the continuous space behind the materials, right? Because I mean, when you do cluster analysis, you kind of discretize them, you force them to have a cluster structure, but very often they have a continuous space behind them.
Yeah.
A related question is that in practice, very often the phenomena people try to observe is actually very rare. So this kind of rare events identification. So especially with the mapper methodology, I wonder, I mean, since you use it for many different applications, some comments on that.
Yeah. So look, so the mapper methodology allows you to use functions that might be of interest concerning the data to either filter it and then also to build the structure. So the idea of anomaly detection, what one might study is things whose whose centrality measure is very low, so to speak, or in other words, is not very central. So that's one way of doing it, and then clustering the things that are only that far out. Another way would be to cluster the things of low density. Take the filter that way and cluster it. We found that at the company, we found that quite useful in many situations. Concerning things like malware and so on. So where one is looking for kind of outliers. So anomaly detection, I think there are some approaches to making that systematic in this way. And so the mapper thing is either you build a model of everything you've got and you look at the things that are far out, or you build a model which allows you to cluster all the stuff that's sitting at a boundary and therefore is, could be expected to be an outlier, an anomaly.
Mm-hmm. I see. How about the using the mapper methodology to explain data behind? Because I don't think you touched upon, but didn't explicitly say it out. So in some sense, a lot of the machine learning method, they are black box.
Yes.
Like approach. I mean, it seems that using some topological method, sometimes you can try to inject some explanation to it, interpretation to it.
So so I will tell you that one of the most black boxy of the machine learning methods is exactly deep learning and neural nets and so on, right? That we don't have good ways of diagnosing that. Now, what we have done here is we've kind of said, I think I showed you the example. Let me go back to it. Here. This one right here, where what we found was that the densest stuff is concentrated around a Klein bottle. And now you could ask, suppose that I'm looking at a convolutional neural net, which has got features in it, and there are connections there between layers, between convolutional layers, that actually look very much like the connections between pixels. In fact, they are. And so within there, you can talk about weight vectors, and the weight vectors are exactly the same as image patches. So there would be, if you take 3 by 3, they would be a 3 by 3 array. So there would be 9 numbers, 9 weights. And what's very interesting is that we did a topological analysis of the weight vectors of high density within a convolutional neural network. And we compared it to this analysis that we have here, and it's exactly the same.
I see.
But my point is that that may by itself not be so surprising, but what it does indicate is that if you do this analysis of the weight vectors, what you can perhaps do is to start to diagnose what's going on in situations where you don't know what's happening. So yes, I think that the mapper and the persistent homology are both potentially very useful for studying what's happening inside the neural nets, because those are very big data sets, a lot of neurons, a lot of activations, and so on.
Right. So actually that brings me to, I think recently you did some work on combining persistent homology or using either persistent homology or mapper to understand the deep neural networks. I mean,
what's to my mind, what's really exciting about it here is that also one can use the topological models to drive architectures. So you drive computational architectures. And so what we've found is that we can actually improve the performance of the neural net dramatically, both on the amount of data that's needed, which is much less for us, and generalization. That is to say, can I evaluate on one data set of images and then, train on one data set of images and then go to another data set and evaluate? That's usually a hard problem. But here you get, for free, you get very much improved generalization without going out and doing transfer learning on other sets and so on.
And would you mind say a bit more? I mean, how is that generalization?
So generalization, so it is a
right now. How is that achieved using topological? So is it that you?
Let me go back and talk a little bit about the problem. The problem is that so here's an example that happened recently for one of the self-driving car companies. So obviously one of the things that a self-driving car needs to have is it needs to be able to take an image, and if it sees a speed limit of 35, it needs to keep the car below 35 miles an hour. So now someone had modified this number 3, so there was a 35, they had modified the central prong, so it was a little bit longer. But the AI in there, the AI read it as 85, and that's a big problem. And so and what that goes to is that's what I would call adversarial examples, but it also goes to generalization. So the idea is that when we restrict further the features that the properties of the features that the neural net uses, it starts to choose the features that we as humans use, and it doesn't, go to overfitting as much. And so therefore, when I've trained that model, it's now ready to do a better job of seeing what's happening in another model, because we've kind of fed it the good features first, and we've also kind of told it that you want to be looking for features that are kind of roughly in this general domain by restricting the connections.
I see. So intuitively, you're saying that using topological features, both somewhat adding the two, a somewhat constraint, somehow it is more robust, and you cannot just because the standard CNN-like architecture probably do sort of pixel-wise error, but here you have a view of the global structure, so make it more robust to such adversarial examples.
Yeah. Actually, let me show another example here, if I may. I realized I had been reading my time here on the screen, and of course, I didn't realize how much time I had. So sorry about that. But let me go back, because I can now talk about one of these other examples, which is relevant in this situation. So, okay, so. Yeah, so this one right here. So, and this is another way of thinking about the topological modeling of the feature space, okay? So I think I showed you that for, for the breast cancer, and I also showed you for the gut biome. But it turns out that it actually has implications for banks. So an example that we did, with Citibank. So Citibank had failed its stress testing process for, a couple of years in a row, and it was bad consequences for them, frankly. And the reason that they had failed is they had done sort of ordinary machine learning on a bunch of features. So the features were actually thousands of features, which are kind of various economic sensors all around the world, and in various domains. And they had simply fit some kind of regression model to it and said, hey, this is predictive, because they had trained on it and they saw that they had managed to get the error down. The regulators looked at it and they said, yeah, you may think it's that way, but we don't understand it. We think you may have been overfitting. We don't know. We don't have no reason to believe that this is, to trust this. And so they failed for that reason. So the argument here, and this goes to your point, Yusu, about understandability of things, that one needs smaller understandable models. And so the feature space idea that I mentioned before is now can be done like this. So in this case, what you see is the model of the feature space. So this is all these different financial measurements. And what you can do now is you can color it. You can take its correlation with the the revenue for a particular business unit. And this is one of those business units, and color by that. And so what you can see here is that there are some high points. There are some high areas of correlation, and so but importantly, each of those high points is itself a group that is pretty consistent, all of them with each other. And so here it makes total sense to say, okay, actually I'm going to build a model with 4 features, and the 4 features are going to be either the average over that group, or I just choose one at random, or maybe choose the highest correlation, whatever, within the groups. And so now you build a sort of a 4D model, which is something more physics-like, that one can perhaps understand. You will pay a small price in the accuracy, but that's just the same price you pay even with deep learning and so on, where, you find you're able to drive things to 99.5% accuracy, but it's not so meaningful because you've got so many variables that you're in, and so much flexibility that you're overfitting. So here now you're going to lose a little bit of accuracy, but you don't believe these models are going to be totally accurate anyway. You kind of want to understand things directionally. And so when we built these models for them, instead, they were actually, the regulators were able to accept these models because they could be justified. And the reason they could be justified is you can see here that each of those boxes, there are some sample measures in there, and the regulators could look at those and see, yeah, I see the 4 features, and not only that, I see that group A is consistent. I see why those all are the same. I see why the group E all are the same. So anyway, that's another situation here. This whole idea of using the geometry of feature space, I think maybe we should give it the name, or actually Michael Robinson, I think, has given it the name, topological signal processing. That is to say, you turn every data problem into something that's like, radar or whatever, where you have a geometry on your feature space, and you use that in a serious way.
Very interesting. All right. And other questions from anyone else?
Yeah. Professor Carlsson, can you give some references for what you were saying about using the TDA for machine learning?
For deep learning? Yeah.
The particular things you were talking about?
Absolutely. So if you go on archive, well, there's a paper of mine with a student named Rickard Gabrielsson. Actually, we have 2 or 3 papers, and so if you find those, you can look at them. One is called Topological Methods for Deep Learning, and the other is something like Exploring or Finding Structure in Deep Learning. They're also, it's actually come out in a book. So the ABEL proceedings, the ABEL Symposium proceedings from 2018 has that paper in it, which is kind of summarizes it all, and also talks about how do you use it to build, how do you use the neural networks, or sorry, the topology to build neural networks.
Thank you. That's great. Thank you.
Anyone else?
I have a question.
Yeah.
Hi, Gunnar. Could you please turn back? Hi, good to see you. Could you please turn back to your last or second last slide?
Yeah, okay. Yeah.
Okay.
Let's see.
Yeah.
Right.
Okay, now okay. Well,
that one?
Right. This thing that you mentioned about the curves and hierarchical structure. Yeah. Could you please elaborate on that? Next slide.
Well, it's a little okay. So what? Pardon me. Yeah, I know. I'm sort of taking their word for it here. I have to say, what I would say is that these, these curves indicate that you've got some loops, and the loops are getting a little bit smaller, then maybe a little bit larger, and they may be contained in each other. The truth is that I was taking their word for the fact that this corresponds to the hierarchical structures. I can't give you a detailed answer on that, unfortunately.
Okay, but would you think that in these clusters there are even further refinements so that you have several tiers?
I think it might be. I think that's what. Yeah, I think this is a place that's actually where it's very likely that one can build more complex diagrams, and that they would capture that, that one would be explicit about where the hierarchy would come from. In other words, that you can see that things one contained in the next. Okay. I think they're seeing a hint of it here in the ordinary persistent homology, but I bet that a more complex diagram might do better.
Yeah. Okay. Yeah. Because that could be quite interesting also in neuroscience, for example.
Mm-hmm.
But I mean, that's a different topic. Yeah.
Right.
Okay. Thank you. Yeah.
Yeah.
I actually have a question.
Mm-hmm.
So
going back to actually, you made the comment about signal analysis. Something I found interesting is the mapping space, right? And how do you map the signal?
The feature space.
Right. And what's interesting is you can tweak some parameters and maybe you capture different information, right? Data might be holding a lot of different things. Do you have anything to say about that in general? I've seen it. Where I've seen it is actually in signals, but in data that's not a signal, that's already in RN, most of us just take it and start applying these methods. Is there anything about looking at maps of this into other spaces and capture?
Well, yeah, so I think there is. You see, I think my point is that you always, so if I have a data matrix, I always have some kind of structure on the set of features, because they themselves are vectors of the same dimension. So I could take an L2 distance, for example. And so if I build a topological structure on top of that, which compresses it, it's a clustering, but with edges between some of the clusters, all of a sudden I can view the original data points as not just long vectors, but as functions on this geometry. Right. And so what that buys you is, like, for example, people have been working on wavelets on graphs. What that is, that uses the graph Laplacian. And I can build bases that are orthonormal with respect to that. And then maybe I study the ones with low eigenvalues first. I see. Something like that. So the whole thing becomes much more structured, because every data point is regarded as a function on some space instead of just as some enormous vector. And so to my mind, this is, this gives you methods of dimensionality reduction, right? Because each one of these models will produce those features, because I can take average over each of the nodes of those features. So anyway, I think there's a lot to be done there. And I think, whenever you can impose geometry on something like that, you now have a better understanding of what the relevant features are. You can start to do things like Fourier analysis, where you introduce higher modes only after you've introduced the earlier modes.
Okay, thank you.
Yeah, thank you so much. This is very interesting from material science perspective. So for any last questions, actually, I am now taking over, since Yusu had to leave.
Oh yeah.
Basically, I have a very quick question here. So this is quite a general problem in material science to connect geometric features of molecules, assemblies, nano and microstructures. And so do you have some or which properties from a material science perspective do you think are easier to predict, and maybe which ones could be more difficult to predict?
I don't, unfortunately, my problem is that I have limited knowledge of solid state physics and of material science. So it's hard for me to know. What I would, again, I would refer to the paper by Hiraoka. It's a PNAS 2016 paper. Where they have a much more detailed discussion of it. I think that might lead to that. As Niels was mentioning, though, I think one of the things is that there are so many more things that you can measure about data than about ordinary topological spaces. There's many different kinds of, diagram things that one could do. So I think a great way for material scientists and topologists, or computational topologists, to interact would be where the material scientist has this feeling in the pit of their stomach. They say, I feel like I want to try to measure this or that, but I don't know how to do it. And I think at that point, then topologists have a rather large toolkit. And so we could sort of propose things and say, well, if that's what you're looking at, I kind of bet we could detect it with this, and then we could try it. And that would be a learning thing, because it would be beautiful to do this, because it would guide the development of the toolkit of topology as well, because you're kind of telling us what are the problems that you really want to address.
Yeah, thank you. That's a great suggestion. Yeah. And there are many instances where it's really difficult, for example, from imaging or diffraction data, or so to extract all these local topologies, and maybe the information is partially known, but part is missing, and then
let me ask, is hyperspectral imaging something that's very interesting in this regard?
It could be. I also, I'm not expert exactly there, but I think it would be.
There are some people who have been thinking about the TDA as used with hyperspectral imaging. Is the only reason I bring it up. I became aware of them a couple of years ago when I was still at IASD, and so a fellow named Duponcel, Duponcel.
Great. So do we have any final questions from anyone?
Yeah, if I may. Hi, Gunnar.
Hi, Paul.
So, you know, when working in material science, there's always this issue of a lot of symmetries, a lot of group action, and that's something we still cannot capture quite well with TDA. I was wondering if you have any thoughts of possible directions or what we can do in order to capture it more properly.
Well, what I would say is actually, I think we just haven't done it in TDA because we haven't seen the need, I think. I actually think that what might be relevant is in these crystallographic situations where we could understand it, where there are groups acting and so on. You know, we could try to do some kind of a persistent, you know, equivariant homology and so on. So I think that there's actually quite a bit of possibility for doing something there.
Agree. Thank you.
So, yeah. Last call, anybody? Well, then, yeah, please go ahead, Steve.
I just have a curiosity question. Has anyone using it to predict the election outcome?
Well, that's a sure way to get your subject killed, right? You know, you'll make a wrong prediction and then they'll say, no, it's no good for anything. But what I will say is I did an analysis a few years back of the World Values Survey. So the World Values Survey is a survey where you study, people have answer about 250 questions. And even using a very small number of those features, you know, surrounding trust in institutions, was able to find a very nice map of the US population and also the South Korean and the Russian one. And I will tell you, they all look different. So wildly different, maybe, which is not surprising. So, you know, in the US, there was a lot of establishment, non-establishment, right to left, and so on. In Korea, it was more about faith and labor unions and so on, it turned out. And in Russia, interestingly, it was complicated, but there was a significant group that was characterized by the fact that they did not feel safe in their neighborhoods. For what it's worth.
I see.
Well,
so it does very helpful in that regard by identify those groups.
Well, what I do think is actually, I would have, you know, it would have been, for me, it would have been wonderful if we could get some of these pollsters to actually put in those World Value Survey questions, because what it would say is, see, if you do that, then all of a sudden you can understand who it is you might have oversampled and undersampled and so on, because you know you'll have a map of those people, and the density map would be different for different cohorts. And you know the whole problem with is obviously you know that you can't get a uniform sample. You don't know how to test it. You've got that. It's just kind of by the seat of the pants. People have some theory that says that it does, and maybe if everybody always ask these questions, and then one could then compare the populations on the map, that would be an interesting thing.
Yeah. Thank you. Thank you.
Well, yeah, so I would also really like to thank you, Gunnar, for this beautiful talk and for the discussion. And then also, you know, for agreeing to make your talk available, you know, for sharing. So,
oh, sure, yeah.
So yeah, thank you so much, and thanks also everyone. Perhaps, I mean, Gunnar, would it be okay for you if someone had a specific follow-up question also to contact you? And
oh, absolutely, of course, absolutely. Anyone would love to, and I would love to actually. I would be curious to if there are specific questions along the lines that you mentioned. That is to say, think about things that you're feeling would be interesting to measure, but it's hard to formulate. Would love to hear about that. Maybe we do a collaboration if that's of interest.
That's great. Yeah, yeah. I think also through YouTube we would be in touch. I mean, because we do look into these problems, and I think we will get some interesting. I mean, you know, it could be really. I think the exciting things happen at the intersection of different scientific disciplines.
Couldn't agree more. Yeah, absolutely agree.
So,
all right.
All right. Well, everybody, thank you again so much for for attending today's seminar, and yeah, wish you a wonderful rest of the day.
All right. Thank you. Bye-bye.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Very interesting.
Great. Thanks very much. Okay, so now I'll stop sharing. All right.